equation. Okay. I'm not interested in the shear force because I no need to form the shear force equation. Okay. Once you have the bending moment equation, we're going to use what? The elastic curve already. That's why I'm skipping the shear force equation. Okay. So we're going to form a bend. So we're going to use from A, between point A to point C, we have 0, x, L over 2. Okay. So we're going to go from, so we're going to draw the free body diagram. Okay. So this is point A. Point A, you have an AY over here. And then over here, you're going to have X. So positive shear assumption, M as a function of X. Right? So we're going to, so this is the point. We're going to take our moment. Okay. So we're going to write summation of moment Z anywhere at point X distance is equal to 0. So this will be equal to minus AYX plus by M as a function of X. The whole thing will be equal to 0. Okay. So this is my equation number 1. So we know that M as a function of X is equal to AYX. Right? So we know that that's equal to, and we're going to apply the elastic curve theory. So this is EI d squared y over dx squared. Okay. So this is my equation 1A. Right? Then we're going to integrate. So you have EI dy by dx. So this will be equal to AY x squared over 2 plus by C1. Okay. So this is your equation number 2. Okay. So now if we look at our equation number 2, can we solve anything? Okay. So equation number 2, right? The limits is between what? 0 up to what? So this is up to what? L over 2, right? So we cannot use equation number what? Boundary condition number what? 3. Because boundary condition number 3 is when x is equal to L. And as I want to remind you, the datum is always on the what? Left-hand side. Okay. So you cannot solve anything. Okay. I'm going to divide my paper into 2. We're going to continue. So from here, we're going to integrate again. Okay, so this term over here, we're going to integrate EI y. So this is equal to AY x cubed over 6 plus by C1x plus by C2. So this is your equation number 3. Right? Okay. So let's recap what we have done so far. Right? What we have done so far. So if we look at what we have now, right? What we've done so far, right? If we go back, we look at the boundary condition, we realize that the boundary condition for this case, this is useless. Right? Wait. No, this is not useless. Sorry, this is not useless. This is still useful. Yeah, it's still, sorry, that's not, I do apologize. This is still useful. Okay. Why? Wait, sorry. Yeah, my bad. Sorry, I'm going to call it useless again. Why this is useless? Because we already formed our moment at point X and it's equal to what? AYX. And you don't need to find a constant. There's no C1 or C2 over here. There's no constant at the end of the term. So this boundary condition over here where X is equal to 0, M is equal to 0 is useless. Okay. Now the problem is this: when we call that useless, we are now down to what? So this is not really useful. We are down to 1, 2, 3. Okay, we only have what? We only can legally use 3 useful boundary conditions. Okay, do I need more? We don't know yet, because this question is very different from the previous one. The previous one is we want to find the deflection and we can find the slope. For this case, we only want to find the what? The reaction at AY and sketch the moment diagram. Okay, so for now, I don't know whether it's useful or not yet. Oh, sorry, I don't know, do I have enough boundary condition yet? Okay, so we have to move on. So from here, we can find one of our boundary condition, right? We have formed this one. So we're going to substitute when x is equal to 0, y is equal to 0, and we're going to go substitute into equation 3, right? So we know that when x is equal to 0, the deflection is equal to 0 because at that location, we have a point load. Sorry, we have a roller support. Okay, so this will be equal to, therefore, C2 is equal to what? Not therefore. So from here, we found that C2 is equal to 0. So therefore, we have EIY is equal to AY x cubed over 6 plus by C1x. Okay, so this is our equation 3a. So we found that C2 is equal to. So from here, can we do anything else? Okay, so from A to C, right, from what we have done so far, is there anything else we can do based on boundary condition whatsoever? The answer is no. Okay, so we have formed 3 equations. Okay, and we solve for one constant. Okay, the other one we don't know because we don't know the boundary condition. Now next we go for between. So we are going to look at between point B to point C. So the limit changes now. So now it's L over 2. Right, so this is equal to L over 2 x, and we'll go to L. Okay, so now I'm going to draw the diagram again. We're going to use positive shear, positive bending moment. So this is my point A, and then this is my point C. Okay, so from here to here, this is my X. So we have AY over here. So the distance, so this is equal to omega, right? So we have to sort out the distance first. So the distance from C to here is X minus by L over 2. So that is omega X minus L over 2. And then the distance to the end of X, this distance from here to here, is equal to X minus L over 2, the whole thing divided by 2, right? And then positive bending moment assumption. Okay, so that's your positive bending moment. So from here, we're going to form another set of equation. Okay. So by taking moment again, at point X is where the dot, I'm going to highlight the dot. This is where I'm taking my moment from. All right, the whole thing will be equal to 0. So this will be equal to minus AYX, right? And then plus by omega X minus L over 2 squared, then divided by 2, plus by M as a function of X. This will be equal to 0. Okay, so I will call this my equation. So this is equation number 4. Right. So we will rearrange. So M as a function of X is equal to minus omega over 2 x minus by L over 2 squared, okay, plus by AY x, right, plus by AY x, and then this is equal to EI d squared y over dx squared. Okay, so this is your equation for A, right? Then we are going to, so far so good. No one have question, right? Anyone have question? You guys are okay, right? So this is our equation for A. Then we integrate again, EI dy by dx. So before I integrate, I'm going to expand it. Okay, so this is equal to minus omega x squared over 2. Wait, let me see. Do I need to? Yeah, no, I'll leave the omega over 2 on the outside. So this is x squared minus by xl plus by L squared over 4, right? So this is plus by AY as a function of x. Okay. So, or AYX, not as a function of x, sorry. So now I'm going to integrate, right? So we have EI dy by dx, right? So this will be equal to minus omega x cubed over 6 minus plus by omega L x squared over 4, and then minus omega L squared x over 8 plus by AY x squared over 2 plus by C3. Okay, so 6 AY, let me check again. Okay, so you have AY x squared over 2 minus omega x cubed over 6 plus by omega x squared over 4 minus omega naught x cubed. So this will be my equation number 5, okay, which is correct. So the most important thing, my advice for before the exam, have plenty of sleep, okay? If you don't have enough sleep, it's very easy to make mistake. So you have EI y now minus x4 over 24. Maybe some of you are quicker than me. I think most of you are quicker than me. X cubed over 12 minus omega L squared x squared over 16 plus by AY x cubed over 6 plus by C3x. If I make mistake, let me know, okay? C3x plus by C4. So this is my equation 6, okay? So we're going to use our boundary condition. Okay, we're going to substitute. Okay, so we're going to use. So if we look at our boundary condition, right, we have used this one. Next, we're going to use the theta. So we're going to substitute when x is equal to when x is equal to L, theta is going to be 0 because of the cantilever beam, and we're going to substitute this into equation number 5. Okay, so we substitute that into equation 5. So this is equal to 0. It's equal to minus omega L cubed over 6 plus by omega L cubed over 4 minus by omega L cubed over 8, right, plus by AY L squared over 2 plus by C3. right? So you have C3 is equal to minus AY